Welcome back. In the previous tutorial, we derived the maths behind the product of two Gaussian PDFs. In this section, we are going to implement the real multiplication in Python code and see whether these formulas are working or not. So I have loaded some Python libraries here. In particular, I have loaded a function called Simpson, which is used to calculate area under the curve, and this will be used to calculate area under the PDF. I have once again written down the equation of Gaussian function, and firstly, we are going to generate two Gaussian functions representing likelihood and prior. The first one is going to be called fx, and the second one is going to be gx. And I will first start with defining this x variable, which is starting from -7 and going up to 7 in 1000 data points. So this is basically the x-axis of the PDF. And then I'm going to insert this x in this formula, as you can see here, and also specify value of mu and sigma, and then calculate all the values for fx. So here is the code for that. In this, mu1 is 0, that is mean is 0. Standard deviation is 1, and I have just use this equation given above, and I have just coded it in Python. And then I'm doing, just to be sure whether my PDF is having an area of 1, which is the typical definition of PDF, I'm going to take the same function fx, this fx function, and integrate it over x using this function called Simpson, and hopefully my area under the curve should be 1. So let me just execute this code first. And as you can see, a beautiful PDF is created here. My x-axis is starting from -7 going up to +7. I have a beautiful looking normal curve here, Gaussian curve, and it is centered at 0 because our mean was 0, and it has a standard deviation of 1, as you can see it here. Also, my area under the curve should have been 1. Typically, this Gaussian curve extends from -infinity to +infinity, but for this particular code demonstration, I have restricted it to -7 to +7. So I've, ideally speaking, I should have integrated it over the infinities. But for practical purposes, I've just integrated it from -7 to +7, and it is giving reasonably well accuracy. The theoretical answer should be 1, but I'm getting 0.99, which is good enough for the purpose of demonstration. So our fx function, which is representing likelihood, is functioning fine. I just repeat the same code to generate another Gaussian distribution to represent the prior, and I'll call it gx. Here my mean is centered at 1, and my sigma is 1.5. And I am again going to repeat the same formula what is given in this equation, and plug in the value of x, which is specified here, and mu and sigma in this equation, and generate the gx function. And then I'm going to calculate area under the curve, and if the area is 1, then my code is working fine. So as you can see, I have to enable a plot here, and I read on the code. So as you can see, this orange curve is the gx function. And as expected, it is shifted from the mean. You can see it is at 0.5, which is what is specified. Sorry, it's at 1, which is what is in the plot, and it has a sigma of 1.5. So obviously, this will be a flatter curve in comparison to the first one. So this is 1 here, centered at mean, and with a sigma of 1.5. So you can treat these two curves or two PDFs as likelihood and prior in the base formula. And once again, my area under the curve is 1, so everything is working fine. Now I'm going to multiply these two functions together in this code. So here is the multiplication, fx into gx, and this will generate a function called hx. And in this, then I'm going to calculate area under the curve, and you will see something very strange happens here. Let me just first run this code and show it to you. So I need this plot of hx. So when I run it, something really strange happens. My PDF, the hx is like this. It is very, very small, and the area under the curve is not 1. So this is because I have not undertaken the normalization. And what I mean by normalization is that to get the area under the curve as 1, I need to divide this whole PDF by this area. So once I do that, so this was the area, and I have taken the PDF, and I have divided the PDF with the area to get the area under the curve as 1. And then recalculated this, and I call it as hx normalized, and I calculate the area under this normalized curve using this integration function, where I supply this PDF and integrate it over x, and then print the results. So let me just run the code once again, and also enable its plot. So when I do that, something very interesting happens. This small PDF here in green color has become very peakier, as shown in this red color. And the area under the curve of this normalized hx is now 1. So this is the correct representation of the hx normalized. And as mentioned in the previous video, where I derived the formulas for sigma h and mu h, you can see that this mean of the product, that is hx normalized, is lying in between the mean of blue and orange PDFs, that is fx and gx, and its variance is lower, which means the curve will become peakier, in comparison to both sigma 1 and sigma 2, that is fx and gx. So let me just disable the unnormalized plot for the clarity sake. Perhaps you can see it now much better. So the blue one is the fx, the orange one is gx, and the green one is the product of both fx into gx, which is normalized by the area, which is this green one. And you can clearly see that the mean of this normalized hx is lying between the means of fx and gx. And since its variance is lesser than both these fx and gx, the PDF is peakier, which means the uncertainty in the system is reduced. So this is as far as multiplication is concerned. I now would like to calculate this the mean and sigma of hx normalized, as shown in the previous video where I derived those formulas. So firstly, let me go through the typical definition of mu and sigma, which is essentially I take the PDF, multiply it by the x values, and integrate it over x. This should give me the mean of the normalized PDF. This is the typical definition of mean of PDF. And then I'm going to do exactly the same thing to calculate sigma, where I'm going to take the PDF itself, normalized PDF, multiply by this, that is x minus mean raised to the power 2, which is the typical definition of the variance. And then I'm going to integrate this entire function over x to get the area under the curve. And since we are interested in standard deviation, that is sigma, not the variance, so I'm going to take a square root of it and then print the results. So this is from the first principles. I'm going to calculate, since the PDF is known to me, from the first principles I'm going to calculate mu and sigma for the normalized hx. So here I am. So I can see that my mu normalized is 0.307 and my sigma normalized is 0.83. Now, if you remember, my sigma 1, that is fx1, was 1 and my sigma 2 was 1.5. And what I finally got after the product of these two functions is that my sigma is 0.8, which is lower than 1 and 1.5. So this is, since the variance is reducing or the sigma is reducing, the curve will become peakier and peakier, and uncertainty and noise from the system will get eliminated. Now this is as far as the derivation from first principle was concerned. I'll go back to the maths of the previous video where formulas were derived for this new mu and sigma, that is mu h and sigma h. If you recall, this is what was equation 4 and 5 were the formulas for the hx function. So I'm going to implement these two in my code and see whether my results are matching or not. So here, if you remember, for the variance part, I had sigma 1 square into sigma 2 square divided by the sum of both of them, as shown in the slide, as shown in the math formula here, this one. And then for the mean part, it is the weighted, the means are weighted with the sigmas of the other PDF, and then denominator is just the same, so which is this part. And then I'm going to calculate the theoretical mu and sigma as derived by the formula that I showed you. So here are the theoretical values, and theoretical values through the formulas, like here the mu is 0.3 and here the mu is 0.307, which is matching, and here is the theoretical sigma 0.83, and here is also the same value 0.83. So our mathematical results are matching with the real results, or the results which were obtained through the code by following the first principles of mu and sigma. And this shows a couple of things. Firstly, by multiplying two PDFs which are independent, which is mandated by Bayes formula, that is likelihood multiplied by prior, we are increasing the certainty in the system, which means the variance or the standard deviation of the posterior is reducing, and as a result this posterior is becoming peakier and peakier, and that's how the noise in the system will get eliminated or filtered out. Now I wish to draw the time domain plots of all these three functions. So what I intend doing is that firstly I'm going to bring down the mean of both fx and gx to 0, so that these PDFs overlap with each other and we are able to see the amplitude of these signals clearly in the time domain plot. So let me run this code again and you will see the overlapping PDFs here. So here we are, because now the mean is 0, both fx and gx are coinciding with each other, and also hx normalized is also having 0 mean, but each of them, three of them have different standard deviation. So what I intend doing now is that I'm going to draw samples from all these three distributions. I know they are Gaussian distributions, so I'm going to use a function called normal, and that will give me the Gaussian distribution with the mean mu1, sigma 1, and number of samples, which is 1000 in this case, to give me samples from the function fx. Then I'm going to use the same one for gx, but this time with mu2, sigma 2, and again 1000 samples. And then I'm going to take my normalized hx, which is the product of fx and gx normalized, and then I'm going to draw the samples from this distribution with the theoretical mean and sigma that we calculated in the previous video, the mathematical derivation that was used to derive those formulas, and again 1000 samples here. And then I'm going to generate the plots in time domain. The idea here is that if the noise is reducing in the posterior, that is hx, then it should show in the amplitude. So let me run this code. And as you can very clearly see that blue is fx, green is gx, and red is hx. So as you can clearly see that gx had a larger sigma. So here is gx, and it had the largest sigma, that is 1.5, and fx had a sigma of 1, and the theoretical results, the theoretical sigma for the hx is 0.83, lower than 1 and 1.5, and the mean obviously 0, that can be clearly seen here. So I'm going to use these two values to draw samples, and as you can clearly see, if you see the amplitude, the green has the highest noise level, and with the various outliers crossing this 2 volt amplitude, and down below also -2. And then we have this blue, which is fx. It has a sigma of 1, hence the wild fluctuations in this blue are lesser than green one. And lastly, we have the posterior, that is hx, which is a result of product of fx and gx. And as you can see, this has got the least fluctuations in the signal. The amplitude is pretty small in comparison to both fx and gx, and that clearly shows that the noise has got filtered out in the system. And this is what exactly happens when you make the assumption of Gaussian distribution and use Bayes formula to calculate the posteriors. So I will be discussing about Kalman algorithm in the next tutorial.